Welcome to Mahasri 4 Electric Zone, your Telugu guide for electrical engineering made easy. In this video, we'll learn how a DC generator generates EMF with simple explanation and diagrams. EMF generation in a simple generator. Let's understand how EMF is generated in a simple DC generator. We take a single-turn coil ABCD rotating clockwise in a uniform magnetic field, as shown in Fig. 1.1. Position 1. The coil is parallel to the magnetic flux. No flux is being cut, so the generated EMF is 0. Position 2. The coil cuts some amount of flux. A small EMF is induced, as shown at point 2 in the waveform. Position 3. The coil is at 90 degrees to the flux. It cuts the magnetic field at the maximum rate, so the induced EMF is maximum, as seen at point 3 in the sine wave. Position 4 and 5. As the coil rotates further, the EMF decreases. At position 5, the coil is again parallel to the flux, so EMF becomes 0. Position 6 to 7. Now the coil moves under a pole of opposite polarity. The EMF reverses direction and reaches maximum in reverse at point 7. Position 8 and back to 1. The EMF again reduces to 0 as the cycle completes. So we observe one full sinusoidal cycle of EMF in one revolution of the coil. Why the EMF is alternating? The induced EMF in the coil is alternating in nature because the coil sides move under north and south poles alternately. But we need direct current. That's where the commutator comes in. Action of the commutator. The commutator is a metal ring split into two segments, C1 and C2, separated by mica. The coil ends AB and CD are connected to these segments. Two carbon brushes rest on these segments and collect current. Half rotation. After half a turn, the coil sides change position under opposite poles, but the commutator also rotates, reversing the connection to the brushes. The result? The current direction through the external circuit remains the same, even though the EMF in the coil is alternating. This is how the DC generator converts alternating EMF into direct voltage using the commutator. The brushes help deliver this voltage to the external load. Thank you for watching. If you found this video helpful, do give it a like, share with your classmates, and don't forget to subscribe to Mahasri 4 Electric Zone for more clear and simple engineering concepts in Telugu. Let us now derive an expression for the EMF generated in a DC generator. We define the following terms. Phi, the flux per pole in Webers. Z, the total number of armature conductors. P, the number of poles. A, the number of parallel paths, which is 2 for wave winding, and P for lap winding. N is the speed of the armature in revolutions per minute, or RPM. Eg is the EMF of the generator, that is, the EMF per parallel path. Now let's calculate the flux cut by one conductor in one revolution of the armature. It is given by d phi equals P times phi, that is, small d phi equals capital P times capital Phi Webers. The time taken to complete one revolution is dt equals 60 by n seconds. Therefore, EMF generated per conductor is given by d phi by dt equals P times phi divided by 60 by n, which simplifies to P phi n by 60 volts. Now let's find the total EMF of the generator denoted by Eg. It is equal to the EMF per conductor multiplied by the number of conductors in series per parallel path. That is, Eg equals P phi n by 60 multiplied by Z by A. So the final equation becomes Eg equals phi times n times Z divided by 60, then multiplied by P by A, volts, where A equals 2 for wave winding, A equals P for lap winding. This is the standard EMF equation of a DC generator. It helps us understand how voltage is generated based on machine construction and speed. Hello and welcome to Mahasri 4 Electric Zone. In today's class, we're going to understand the construction of a DC generator, one of the most important concepts in electrical machines. Did you know? The construction of a DC generator and a DC motor is almost the same. When assembling, even the technician won't know whether it's going to work as a motor or a generator. It depends on how we connect it. Let's break this topic into 5 main parts, the 5 principal components of a DC generator. 1. Field system. The field system is responsible for producing a uniform magnetic field in which the armature rotates. It includes a circular frame called the yoke pole cores and pole shoes bolted inside the yoke field coils wound on these poles. The field coils carry direct current, DC, and generate magnetic flux. Poles are arranged in such a way that adjacent poles have opposite polarity, N and S. A smaller air gap between the poles and armature, around 0.5 mm to 1.5 mm, means fewer turns are needed in the coil, making it more efficient. 2. Armature core. The armature core is mounted on the shaft and rotates between the field poles. It's made of thin, laminated soft iron sheets, 0.4 mm to 0.6 mm thick, to reduce eddy current losses, make the magnetic path efficient. The laminations are coated with insulating film so that they don't conduct between each other. 3. Armature winding. This is where the real magic happens. The armature winding is placed inside the slots of the armature core. This is where the working EMF, voltage, is actually generated. The conductors are arranged in a series parallel manner. Series connection increases voltage. Parallel paths increase current. These windings form closed loops so that current keeps flowing continuously when the generator runs. 4. Commutator. Now comes the commutator, a very crucial part. Its job is to convert the alternating EMF generated in the armature, winding into unidirectional DC voltage. It is made of copper segments, insulated from each other with mica. These segments are mounted on the shaft and rotate with the armature. Each armature conductor is connected to a commutator segment. As the shaft spins, the commutator keeps reversing connections at the right time, producing DC at the output. There are 2 common types of winding connections here: lap winding, wave winding, 5 brushes, and finally, the brushes. These are usually made of carbon and rest lightly on the rotating commutator. The purpose of the brushes is to connect the rotating commutator to the external load, transfer the generated DC voltage. If we have a 4-pole machine, we'll typically have 4 brushes, 2 brushes for the positive terminal and 2 for the negative terminal. They are placed so that brushes of the same polarity are connected together. The brushes stay still, but as the commutator rotates beneath them, the connection remains smooth, and that's how we get continuous DC output. That's it! You've now learned the complete construction of a DC generator: field system, armature core, armature, winding, commutator, brushes. This is the foundation for many other concepts in DC machines, so make sure it's crystal clear. If you found this useful, don't forget to like, share, and subscribe to Mahasri 4 Electric Zone. Let's keep making electrical engineering easy and interesting together. Welcome to Mahasri 4 Electric Zone, your Telugu guide for electrical engineering made easy. In this video, we'll learn how a DC generator generates EMF with simple explanation and diagrams. EMF generation in a simple generator. Let's understand how EMF is generated in a simple DC generator. We take a single-turn coil ABCD rotating clockwise in a uniform magnetic field, as shown in Fig. 1.1. Position 1. The coil is parallel to the magnetic flux. No flux is being cut, so the generated EMF is 0. Position 2. The coil cuts some amount of flux. A small EMF is induced, as shown at point 2 in the waveform. Position 3. The coil is at 90 degrees to the flux. It cuts the magnetic field at the maximum rate, so the induced EMF is maximum, as seen at point 3 in the sine wave. Position 4 and 5. As the coil rotates further, the EMF decreases. At position 5, the coil is again parallel to the flux, so EMF becomes 0. Position 6 to 7. Now the coil moves under a pole of opposite polarity. The EMF reverses direction and reaches maximum in reverse at point 7. Position 8 and back to 1. The EMF again reduces to 0 as the cycle completes. So we observe one full sinusoidal cycle of EMF in one revolution of the coil. Why the EMF is alternating? The induced EMF in the coil is alternating in nature because the coil sides move under north and south poles alternately. But we need direct current. That's where the commutator comes in. Action of the commutator. The commutator is a metal ring split into two segments, C1 and C2, separated by mica. The coil ends AB and CD are connected to these segments. Two carbon brushes rest on these segments and collect current. Half rotation. After half a turn, the coil sides change position under opposite poles, but the commutator also rotates, reversing the connection to the brushes. The result? The current direction through the external circuit remains the same, even though the EMF in the coil is alternating. This is how the DC generator converts alternating EMF into direct voltage using the commutator. The brushes help deliver this voltage to the external load. Thank you for watching. If you found this video helpful, do give it a like, share with your classmates, and don't forget to subscribe to Mahasri 4 Electric Zone for more clear and simple engineering concepts in Telugu.
Hello, students. In this session, we are going to learn about the types of DC generators. Let's get started. Types of DC generators. The magnetic field in a DC generator is usually produced by electromagnets, not permanent magnets. Generators are classified based on how the field is excited. DC generators are divided into two main types. 1. Separately excited DC generators. 2. Self-excited DC generators. The load behavior of a DC generator depends on the type of excitation. Separately excited DC generators. A DC generator whose field winding is powered by an external DC source, like a battery, is called a separately excited generator. The output voltage of this generator depends on the speed of rotation of the armature and the field current. The higher the speed and field current, the more EMF is generated. But these generators are rarely used in practice. Most DC generators are of the self-excited type. Here is the circuit diagram. Armature current, I is equal to IL. Terminal voltage, V equals Eg minus IA. Electric power developed is Eg into IA. Power delivered to load is IA multiplied by Eg minus IR, which equals V into IA. Self-excited DC generators. A DC generator whose field winding gets current from its own output is called a self-excited generator. There are three types based on how the field winding is connected. 1. Series generator. 2. Shunt generator. 3. Compound generator. 1. Series generator. In this type, the field winding is connected in series with the armature winding. That means the entire armature current flows through the field and the load. Since it carries high current, the winding has few turns of thick wire with low resistance. These generators are rarely used, only for special applications like boosters. Circuit explanation. Power delivered to load is V into IL. 2. Shunt generator. In this type, the field winding is connected in parallel to the armature. That's why it's called a shunt generator. This field winding has many turns of fine wire and high resistance. Only a small part of the current flows through the field winding. The rest goes to the load. Let's see the details from the diagram. Right shunt field current, ISH is equal to V divided by RSH. Right armature current, I is equal to IL plus ISH. Right terminal voltage, V equals EG minus IA. Right power developed in the armature is EG into IA. Right power delivered to load is V into IL. 3. Compound generator. This is a combination of series and shunt generators. It has 2 field windings on each pole. One is connected in series. One is connected in parallel. Compound generators are of 2 types. A short shunt compound generator. Here, the shunt field winding is connected across the armature only, not across the series field. From the diagram, right series field current, ISE is equal to IL. Right shunt field current, ISH is equal to V plus ISE into RSE, divided by RSH. Right terminal voltage, V equals EG minus IR minus ISE RSE. Right power developed equals EG into IA. B. Long shunt compound generator. Here, the shunt field winding is connected across both the armature and series field. From the diagram, right series field current, ISE equals IA equals IL plus ISH. Right shunt field current, ISH equals V divided by RSH. Right terminal voltage equals EG minus IA times RA plus RSE. Right power developed equals EG into IA. Right power delivered to load equals V into IL. Pushpin note. In all cases, power loss due to resistance is I squared. Voltage drop occurs in the armature and field winding. Efficiency depends on how much of the generated power reaches the load. Direct hit summary. Let's revise the key points quickly. Separately excited generator. Field winding uses an external source. Series generator. Field in series with armature. Shunt generator. Field in parallel with armature. Compound generator. Uses both series and shunt fields. Woman teacher. That's all for this session on types of DC generators. I hope you understood the topic clearly. Like the video, share it with friends, and subscribe for more such lessons. Thank you so much.
Hello students, in this class we're learning about losses in a DC machine, whether it's a DC motor or a DC generator. What do we mean by losses? Losses are the portions of input power that get wasted as heat. They do not contribute to useful output, and they reduce the machine's efficiency. There are 3 major types of losses in a DC machine. 1. Copper losses. 2. Iron or core losses. 3. Mechanical losses. Let's go through each of them. 1. Copper losses. These losses happen due to the flow of current through the machine's windings. There are 3 kinds. First, armature copper loss, which is equal to armature current squared times armature resistance. Say it as IA squared multiplied by RA. Second, shunt field copper loss, which is shunt current squared times shunt resistance. Say I SHA squared times RSH. Third, series field copper loss, which is series field current squared times its resistance. Say ISE squared multiplied by RSE. 2. Iron or core losses. These losses occur in the armature core and are caused by its rotation in the magnetic field. There are 2 types. A. Hysteresis loss. This occurs because the magnetic field reverses continuously as the armature rotates. Every time the core material magnetizes and demagnetizes, a small amount of energy is lost. B. Eddy current loss. This happens when small circular currents, called eddy currents, are induced in the armature core due to changing magnetic fields. These currents produce heat and reduce machine efficiency. 3. Mechanical losses. These are caused by friction and air resistance or windage. Examples include friction loss from brushes or bearings, windage loss, which is air drag on the rotating armature. Together with iron losses, mechanical losses are often called stray losses. Classification based on load. We can also divide all losses into I, constant losses. These do not depend on load. They remain the same all the time. Examples are iron losses, mechanical losses, shunt field losses, Purdy, variable losses. These change with the load. The more the current, the higher these losses. Examples are copper loss in the armature winding, which is armature current squared times armature resistance. Copper loss in series field winding, which is ISE squared times RSE. Total losses. To summarize, we write total losses equal constant losses plus variable losses. That's all for this topic. Next time someone asks what's eating away your generator's efficiency, you'll know the answer. If you liked this explanation, hit like, share, and subscribe to Mahasri 4 Electric Zone for more power-packed lessons. Hello everyone, welcome back to Mahasri 4 Electric Zone. In today's class, we are going to understand a very important concept in DC machines, and that is commutation. You might have heard this word before, but what exactly is commutation? Why is it needed? And what happens if it's not done properly? Let's explore everything in a very simple and clear way. What is commutation? Imagine a DC generator, where the coil keeps rotating between magnetic poles. Now, every time the coil rotates and crosses a brush, the direction of current in that coil has to reverse. This reversal of current, as the coil passes the brush axis, is called commutation. It happens in a fraction of a second, but it's super important. If commutation doesn't happen properly, we'll have problems like sparking at the brushes. So it's not just a concept, it's a real issue in machine performance. The basics. What actually happens? Let me explain with a simple example. We are looking at a two-pole lap-wound DC generator. In this, there are two parallel paths between the brushes. So the total armature current is divided equally. Each coil carries half the current. Say total armature current is 40A. Then each path has 20A. Now look at the brush touching the commutator segment. When a coil comes in contact with the brush, current starts flowing through that brush and commutator segment. But as the armature rotates, the brush shifts and touches the next segment. During that transition period, the coil is connected to both segments. It gets short-circuited by the brush. This short time, where the brush is connected to two segments, is called the commutation period. If current reversal is completed during this period, it's ideal commutation. If not, sparks fly. Ideal commutation. Explained simply. Let's take the case of ideal commutation. What does ideal mean? It means the current reverses completely and smoothly, with no sparking. Here's what we assume. The coil has no inductance. The brush width, we use one commutator segment, plus one mica insulation. Total current, 40 A. So each path has 20A. In step 1, the brush is in full contact with segment 1. It conducts 40A, 20A from coil A, and 20A from the other coil. Coil A hasn't started commutation yet. In step 2, as the armature rotates, the brush begins touching segment 2. Now coil A is short-circuited. Current flows through both segments. Brush splits current depending on resistance. In step 3, the brush is halfway on both segments. Resistances are equal, so current from coil A becomes 0. In step 4, current starts building in the reverse direction. Now 10A flows through segment 1 and 30A through segment 2. Finally, in step 5, the brush is fully on segment 2. Coil A now carries 20A, but in the reverse direction. This whole process, from plus 20A to 20A, is called commutation. Current time graph. Let's now understand the current time graph of ideal commutation. The line AB shows plus 20A, constant before commutation. During commutation, it changes smoothly from B to C. Finally, at CD, current is 20A, it reversed completely. If BC is a straight line, then current is changing at a uniform rate. That's why it is called ideal commutation. No sparks, no heat, no damage. Why is it important? 30 secs. Now you might ask, what if commutation is not ideal? Well, the answer is sparking. When reversal is incomplete, there's a voltage difference between commutator segments. That causes arcing and damages both the brush and the commutator. So proper commutation is necessary for long machine life and efficient operation. Summary. 30 sec. Let's recap quickly. Commutation means current reversal as coil passes the brush. Happens during the short circuit period by the brush. Ideal commutation, by smooth reversal, by no sparking. If not ideal, sparking occurs. The graph of ideal commutation is a straight line from plo 20A to 20A. Now that's a clear and friendly understanding of commutation. Hope you understood this topic clearly. If this video helped you, do give it a like, share it with your friends, and don't forget to subscribe to Mahasri 4 Electric Zone for more such friendly lessons in Telugu and English. Also, comment below if you want me to explain reactance commutation or improvement methods in the next part. See you in the next class. Happy learning.
Hey everyone, welcome back to another interesting session on DC machines. In this video, we'll be talking about two important concepts. Right finger condition for maximum efficiency of a DC generator. Right finger and an overview of DC generator characteristics. Let's break it down in a super simple way, so even if you're learning this for the first time, you'll get it right. Condition for maximum efficiency of a DC generator. First, let's understand something. The efficiency of a DC generator is not constant. It changes depending on how much load we're giving to the generator. So, let's say we have a shunt generator, and it's supplying a load current called IL at a terminal voltage V. Now let's look at generator output equals V times IL. Generator input equals output plus losses. These losses include both variable losses and constant losses. So the total input becomes V times IL plus IL squared times RA plus WC, where IL is the load current, RA is the armature resistance, WC is the constant loss. Now in a shunt generator, there's also a shunt field current, called ISH. But this current is very small when compared to IL, so we usually neglect it for simplification. So again, our input becomes V times IL plus IL squared times RA plus WC. And therefore, the efficiency is given by efficiency equals output input. That is, efficiency equals V times IL divided by V times IL plus IL squared times RA plus W century. This looks a bit complex, right? Don't worry, just focus on this. The denominator, that is, the input, should be minimum for the efficiency to be maximum. So what do? We take the derivative of the denominator with respect to load current IL, and set it equal to 0. This gives us the condition for maximum efficiency. After solving, we get IL squared times RA equals WC, which means variable loss equals constant loss. So finally, the condition for maximum efficiency is when the load current is such that the variable loss equals the constant loss. And the load current at this point is given by IL equals square root of WC divided by RA. Nice and simple, right?
Hello everyone. Welcome to Mahasri 4 Electric Zone. Today we will solve a simple problem based on a DC shunt generator. Let's begin step by step. Problem statement. A shunt generator supplies 96 amperes at a terminal voltage of 200 volts. The armature resistance is 0.1 ohm. The shunt field resistance is 50 ohms. Iron and frictional losses are 2,500 watts. We are asked to find 1. The generated EMF, 2. The copper losses, and 3. The commercial efficiency. Step 1. Shunt field current. We start by calculating the shunt field current. Using Ohm's law, ISH equals V by RSH, that is, 200 by 50, which gives us 4 amperes. Step 2. Armature current. Now we find the armature current. It is the sum of load current and shunt current. IA equals IL plus ISH, that is 96 plus 4, which equals 100 amperes. Step 3. Generated EMF. Now, the generated EMF, denoted by Eg, is given by Eg equals V plus Ia into Ra. Substituting the values, Eg equals 200 plus 100 into 0.1, which gives us 210 volts. Step 4. Copper losses. Let's now calculate copper losses. Armature copper loss equals Ia squared times Ra. That is 100 squared times 0.1, which gives us 1000 watts. Shunt copper loss equals Ish squared times Rsh. That is 4 squared times 50, which gives us 800 watts. Total copper loss is the sum. 1000 plus 800 equals 1800 watts. Step 5. Total losses. Now add the iron and friction losses. Total losses equals 2,500 plus 1,800, which is 4,300 watts. Step 6. Output and input power. Output power equals voltage into load current, that is 200 times 96, which equals 19,200 watts. Input power is output power plus losses. That is, 19,200 plus 4,300 equal to 23,500 watts. Step 7. Commercial efficiency equals output by input into 100. That is, 19,200 by 23,500 times 100. This gives us 81.7%. Final answers. Recap: generated EMF equals 210 volts. Total copper loss equals 1,800 watts. Commercial efficiency is 81.7%. Thank you for watching. For more electrical machine problems and concepts, subscribe to Mahasri 4 Electric Zone. See you in the next video. Hello everyone, welcome back to Mahasri 4 Electric Zone. In this video, we are solving example from DC generators. Let's begin. Problem statement. A shunt generator delivers a full load current of 200 amperes at 240 volts. The shunt field resistance is 60 ohms and full load efficiency is 90%. Rotational losses are given as 800 watts. We are asked to find, first, the armature resistance, second, the load current at which maximum efficiency occurs. Let's solve step by step. Step 1. Generator output. Output power equals voltage times current. So generator output equals 240 multiplied by 200, which is 48,000 watts. Step 2. Generator input. Since efficiency equals output divided by input, we can rearrange the formula to find input power. Input equals 48,000 divided by 0.9, which gives us 53,333 watts. Step 3. Total losses. Now subtract output from input to find total losses. Total losses equals 53,333 minus 48,000, which is 5,333 watts. Step 4. Shunt field current. We calculate the shunt field current using Ohm's law. ISH equals V divided by RSH, that is 240 divided by 60, which gives 4 amperes. Step 5. Armature current. Armature current is the sum of load current and shunt field current. IA equals 200 plus 4, which gives 204 amperes. Step 6. Shunt copper loss. Shunt copper loss is given by I squared R, so shunt loss equals 4 squared multiplied by 60, which is 16 times 60, equal to 960 watts. Step 7. Constant losses. Constant losses are the sum of rotational and shunt copper losses. Constant losses equals 800 plus 960, which is 1,760 watts. Step 8. Armature copper loss. Now subtract constant losses from total losses. Armature copper loss equals 5,333 minus 1,760, which is 3,573 watts. Step 9. Armature resistance. Use the formula I squared R to find armature resistance. RA equals armature copper loss divided by IA squared, that is 3573 divided by 204 squared, which equals 0.0858 ohms. So armature resistance is approximately 0.0858 ohms. Step 10. Load current for maximum efficiency. Now apply the condition for maximum efficiency. At maximum efficiency, variable losses equal constant losses. So IL squared multiplied by RA equals 1,760. Rearranging, IL equals the square root of 1,760 divided by 0.0858, which gives 143.22 amperes. So maximum efficiency occurs at a load current of 143.22 amperes. Final answers. Recap.